Row reduction. Row reduction is a four-step algorithm used to produce a matrix in row echelon form. This algorithm is also known as Gaussian elimination. A fifth step can be added to produce a matrix in reduced row echelon form. In this case, the algorithm is called Gauss-Jordan reduction. We're going to use an example to walk you through the algorithm of row reduction. I'm going to show you how to do both Gaussian elimination and Gauss-Jordan reduction using this example. So let's start with a linear system of three equations and three variables. And let's also write down the corresponding augmented matrix for this system. Step 1. We find the leftmost non-zero column first. That's the column 0, 1, negative 4. It's a non-zero column because it has some non-zero entries. The 1 and negative 4 are non-zero entries in that column. This column is called a pivot column, and the topmost position is called a pivot position. Step 2. We select a non-zero entry in the pivot column. Let's use this entry, the 1. That's a nice non-zero entry in the pivot column. If this entry is not in the pivot position, then we interchange rows. Okay, notice that the 1 is not in the pivot position. It has to go one row up. So we're going to interchange rows 1 and row 2. And we get this matrix. Notice that the first row of the new matrix is the second row of the old one. And similarly, the second row of the new matrix is the first row of the old one. We just interchanged those two rows. Notice also that the 1 is now in the pivot position. And in this case, we call the number 1 a pivot. Step 3. Create zeros in all positions below the pivot using row replacement operations. So below that pivot of 1, we need to have zeros. That negative 4 in particular needs to be changed to a 0. So we start by rewriting the first row, because remember, the pivot row never changes during a row replacement operation. So we could just rewrite it. And we could also rewrite the second row in this case, because there's already a 0 in the position below the pivot. We need to change that negative 4 into a 0 using row replacement. So we're going to be changing row 3. Row 1 is the pivot row. We'll multiply row 1 by 4 so that the two numbers match up. We'll have a 4 in row 1 and a negative 4 in row 3. And if we add those numbers, we'll get 0. So our row replacement operation is row 3 plus 4 row 1. Let's do this column by column. For the first column, we have negative 4 plus 4 times 1 is 0. For the second column, we have 5 plus 4 times negative 2 is 5 minus 8, which is negative 3. For the third column, we have 9 plus 4 times 1 is 9 plus 4, which is 13. And for the fourth column, we have negative 9 plus 4 times 0 is negative 9. Step 4. We ignore the row containing the pivot position and all rows above it. That's the first row. So I put a light yellow line through that first row to indicate that we're going to ignore it from now on. And now we repeat steps 1 through 3 on the remaining submatrix. So we're just looking at the submatrix consisting of the bottom 2 rows now, and we repeat the procedure. Let's go back to step 1. We find the leftmost non-zero column. There we go. So we see we have this pivot column consisting of 2 and negative 3, and the pivot position is where that 2 is. Step 2, we're going to select a non-zero entry in the pivot column. We might as well just go ahead and choose that 2 since it's already in the pivot position. So no need to interchange rows this time. Step 3, we have to create zeros in all positions below the pivot using row replacement operations. So we need to change that negative 3 to a 0. So we're going to be doing Let's see, row 3 is the row that's changing. Row 2 is the pivot row. We multiply row 3 by 2 and row 2 by 3 to make them match up at 6 and negative 6. And if we add them, they'll cancel out to 0. All right, so let me go ahead and rewrite the first 2 rows. We're rewriting the first row because it's being ignored and we're just letting it sit there. And we're rewriting the second row because it's the pivot row. And again, the pivot row does not change during a row replacement operation. We could just throw in those first 2 zeros. Hopefully you see that those entries are 0. And let's do the last 2 columns. So we have 2 times 13 plus 3 times negative 8 is 26 minus 24, which is 2. And let's just pop that into the third entry in the third row there. And the last column here, 2 times negative 9 plus 3 times 8 is negative 18 plus 24, which is 6. And we'll put that into the last entry in the third row over there. And now we go to step 4, except we don't really need to go to step 4 because the matrix is already reduced, right? It's in row echelon form. Okay. The corresponding system of equations for this matrix is x minus 2y plus z equals 0, 2y minus 8z equals 8, 2z equals 6. We now have 2 options here. We could continue to reduce this matrix to reduced row echelon form. For that, we'll need a 5th step, and I'm going to show you how to do that a little later. But first, let's go ahead and solve this the other way using back substitution. So I'm going to start with the third equation and divide each side of that equation by 2 to get z equals 3. Now to the second equation. We have 2y is 8 plus 8z. Replace z by 3, and we get 8 plus 8 times 3, which is 8 plus 24, or 32. So we have 2y equals 32. Dividing by 2 gives us y equals 16. And now the first equation, x is equal to 2y minus z. Replace y by 16 and z by 3, and we get 2 times 16 minus 3, which is 32 minus 3, or 29. Okay, so to summarize, we started with our linear system, wrote the augmented matrix for that system, row reduced using the 4-step row reduction algorithm, or equivalently Gaussian elimination, and then used back substitution to find x, y, and z. Now, instead of doing it that way, we can add a 5th step to the row reduced matrix to get a matrix that's in reduced row echelon form. The 5th step is to create zeros in all positions above each pivot using row replacement operations. Okay, so let's start with this pivot, the rightmost 2. We have to get zeros above that pivot, so we want to change the 1 and the negative 8 to 0. I'm going to start by rewriting the pivot row because again we're going to be doing row replacement operations and the pivot row does not change when we do those operations. Let's start with the first row. We're changing row 1. Row 3 is the pivot row. We multiply the first row by 2 and then subtract so that it cancels out to 0. Column by column, we have 2 times 1 minus 0 equals 2. 2 times negative 2 minus 0 equals negative 4. 2 times 1 minus 2 is 0. And 2 times 0 minus 6 is negative 6. Now let's take care of this negative 8. We're changing row 2. Row 3 is the pivot row. We multiply the pivot row by 4 to make them match up at 8 and minus 8, and add to cancel to 0. So our row replacement operation is row 2 plus 4 row 3. Again, column by column, we have 0 plus 4 times 0 is 0. 2 plus 4 times 0 is 2. Negative 8 plus 4 times 2 is negative 8 plus 8, which is 0. And 8 plus 4 times 6 is 8 plus 24, which is 32. Okay, let's go left 1 to the next pivot, which is the 2 in the second column, and we have to change that -4 to a 0. We can rewrite the pivot row because, again, the pivot row does not change during a row replacement operation. That's the second row there. And we could also rewrite the third row because it already has a 0 below the pivot. So now we're going to be changing row 1. Row 2 is the pivot row. Multiply row 2 by 2 to make them match up at 4 and -4, and add to cancel to 0. So starting with the first column, we have 2 plus 2 times 0 is 2. -4 plus 2 times 2 is -4 plus 4, which is 0. 0 plus 2 times 0 is just 0. -6 plus 2 times 32 is -6 plus 64, which is 58. Great. Now we could finish this up by simply using scaling operations to make all the pivots 1. So those 3 2's along the diagonal, we're going to change them to 1's by scaling. So we could do 1/2 row 1, 1/2 row 2, and 1/2 row 3. And this is pretty simple. This is equivalent to just dividing all the entries by 2, and we get this matrix. Notice the right-hand column becomes 29, 16, and 3. So this matrix is now in reduced row echelon form, and we could just read off the solution. X equals 29, Y equals 16, Z equals 3. Again, if we add in this step 5, then what we have done is Gauss-Jordan reduction.